to solve complex problems in the industry. And then everything you see here is all about some of the case studies which I will be covering, which are based on real world case studies from the industry in terms of, and you can see by looking at the names, like I will not just be covering problems from, let's say, one domain, like only talking about e-commerce problems, but I will be talking about at least 5 to 6 different types of domains or industries. Like we have data center device failures around infrastructure. This is around healthcare. Security vulnerability detection is in cybersecurity. Image super resolution, neural style transfer are complex computer vision problems. And then we have anomaly detection again, which is more of a time series problem, can be used on any kind of data, manufacturing, time series data, and any industry working with temporal data. So since I've already been introduced, I will not waste too much time talking about myself again. But as I've already been introduced, I work as a lead data science consultant. I have also been associated with different Fortune 500 companies, and I have worked on AI initiatives, starting from a data scientist and then growing up till a lead data scientist. And I am also associated with different universities and organizations in terms of ramping up companies as well as personal professional people to learn how to leverage AI for their own needs, be it professionally or personally. And I'm also a part of different executive education programs related to data science and AI. So coming to the first part of the session about learning basics. So why do we need learning and what is learning all about? So the need for learning is to solve increasingly complex problems which humans can solve easily thanks to their brain and all the advanced cognitive capabilities which the brain, along with the rest of the human body, consists of. So as you can see, these are some examples where if you look at these images, you can easily recognize what is a dog or what is a mop. But if you try to train a machine to do this, it can become a challenge. Same with the image you see on the right-hand side. So this is where these are problems which can't be solved by traditional programming approaches. And in traditional programming approaches, basically, we had inputs and we had a program which we sat and coded with fixed rules and logic, and then we obtained some kind of a final system which used to be used or deployed like a traditional software engineering system. But nowadays we are moving from hard-coded logic and rules towards data-driven programs where we leverage models like machine learning or deep learning models to solve increasingly complex problems like image recognition, object detection, natural language processing, speech processing, robotics. And I mean, the possibilities are endless. And the whole point of doing this is to make machines learn, comprehend, and understand and extract useful semantic information from large data sets or small data sets, depending on the nature of the problem. And this is where we need models to learn from data and basically try and reach to that level of human intelligence, because we as humans are constantly thinking, like as you are listening to me talk right now, uh, involuntarily you're thinking about a bunch of things because that is what we are capable of. We can comprehend and understand and pick up things really easily because of our years of experience, but a machine can't do that. It has to be taught based on data and models. And that's where we are trying to see what is the best we can get in terms of the current technology which we have. Some basic terminology, which I think most of you are already aware about. So AI is basically any kind of intelligent system which can perform a task which is complex and not very trivial. Machine learning is one of the techniques, or you can say approaches, which can be leveraged to build AI systems where these models increasingly become more and more intelligent as you feed it more data by learning patterns from data automatically. You're not hard coding the rules. And deep learning is a specialized area of machine learning, which does exactly the same thing as machine learning models do. But they are multi-layered neural networks, which scale and perform better with larger and more complex data sets. And in terms of the types of learning, we have supervised learning where you may have label data. So it's like if you have historical house price data, you can predict the price of a house in the future, given that you have the right features for that house. You have unsupervised learning where based on a given data set and a high level objective in mind, we try to find out similar items, do some recommendations or group similar items together and find out insights from different clusters. So that is all about pattern mining, clustering, and finding out insights from data which is not labeled. And reinforcement learning is dynamic learning where we try to train an agent based on a surrounding environment to automatically learn from mistakes or learn from rewards, and based on that, try to achieve a goal. And then we have neural networks where the inspiration is coming from the human brain. Just something to remember, replica of the brain, because the brain is a really complex artifact which scientists are still trying to decode how best humans learn. So neural networks is just an approximation, and is just, you can think about it like the first or the second step towards seeing or replicating how the human brain works. So the inspiration has been taken from the neurons which are present in our brain. And the whole point here is we try to take in different features. We try to perform some kind of a linear approximation here, and then we apply a nonlinear activation function, which is one of the key perspectives of a neural network, where in each neuron you apply a nonlinear activation function to capture different kinds of nonlinear patterns in the data, because most kind of trends in the data these days are nonlinear. And that is where neural networks can act as universal function approximators. They can pretty much approximate any kind of complex function given enough data. And the nonlinearities help the neural network model to learn different types of features automatically without you sitting and hard coding features. And then you have the training for neural networks, which I think a lot of you might be aware about. But just as a recap, you start with some data, you may have some labels for it, you forward the data through the network to generate some predictions. You compare your predictions with the actual labels, you compute the loss, you compute the gradient of the loss with respect to each layer from the back to the front. Hence, it's known as backpropagation, because you backpropagate the errors back to each and every layer and update the weights of the neurons in each and every layer. And this process continues again and again till we reach convergence, or when the model performance starts degrading. And that's why deep learning is kind of machine learning on steroids, because for most problems, you need to spend enough time in handcrafting features in machine learning problems. Like, let's say you are doing a image classification problem. Image classification is nothing new. It has been solved even several years back by traditional computer vision techniques, where we used image processing. We manually used edge filters, corner filters, uh, resolutions, brightness, contrast, different types of convolution kernels used to be used manually to extract relevant features, feature descriptors like surf, sift, and so on. And then we used to feed it into a model like an SVM and do classification. But nowadays, thanks to convolution neural networks, you can automatically do everything: feature extraction, classification, detection, um, denoising. So applications are endless. And in terms of the terminology, again, there is no fixed thing here. What people tend to think is that if you have more than 3 or 4 layers of hidden layers in a neural network, it's termed as a deep network. Otherwise, it's often termed as a shallow neural network. In terms of effectiveness as to why is deep learning becoming more and more prominent and important in the industry, there are several reasons for this. If you see, the adoption of deep learning is massive, because nowadays AI has become a marketing term, sadly. But in my opinion, AI is something where you're trying to build a system which can perform a complex task, which is not that easy to solve using some kind of a trivial model. So the closest we have got to AI is, I think, by leveraging deep learning. But true AI is basically one step ahead of deep learning, where you have things like continual learning or lifelong learning, where the model continuously learns with more data automatically. But we are not there yet from a complete industry perspective everywhere. But where we have reached is deep learning has increasingly been adopted across diverse domains in the industry. As you can see, in terms of consumer domain, you have things like smart assistants, personalization being done where you get recommendations based on your personal profile, customized search, chatbots, augmented reality, virtual reality. So all of these things are relevant to how consumers are consuming goods, services, content, and so on. You have healthcare where you have medical imaging based use cases, which have definitely cracked a lot of tough to solve problems of disease diagnosis. You have drug discovery, which is something where you can leverage generative models as well as reinforcement learning to generate new drugs, which would otherwise take a lot of time, let's say several years back. Now you can fast pace that. And then you have aspects in finance, obviously, where people are leveraging extensively time series forecasting based models on deep learning, as well as reinforcement learning to find out how do you trade in the best way, how do you maximize your return, how do you minimize the risk, fraud detection, risk mitigation, all are popular problems where increasingly deep learning as well as elements of machine learning are being used. And then we have aspects like retail, where we obviously in the e-commerce industry as well as retail, a lot of things in sales, marketing, supply chain, logistics, customer retention. So definitely a lot of use cases again in retail where AI is playing a part. And the best part nowadays is usually these things used to take a lot of time for governments to adopt because, again, they are busy in a lot of other things, let's say, not really with the emphasis on adapting to new technology unless, let's say, it will benefit the community. So, in that way, now we are seeing in terms of defense, data-driven insights. As you know, almost every government, including in India, we have a data.gov portal with all kinds of open data and insights analysis being present. Smart cities is something which is becoming bigger and bigger in almost every country, and that is where AI, Internet of Things, edge devices. These are things which will definitely play a big part and are playing a big part. In fact, uh, there are several people who sometimes think that oil and gas is an old industry where AI is not being used. But if you look at some of the latest research as well as implementations, people are even starting to use, not starting, but have actually started using AI-based systems for several years now to find out when should I stop drilling when I am trying to drill in an oil well? When do I know that the drill bit can basically explode or uh, there can be a defect? How do I maximize the yield? So yield maximization, manufacturing, all these aspects in terms of oil and gas are definitely seeing increasing use of AI-based systems. In transportation, again, it's mixed. Like we have kind of tried to crack self-driving, but it's still not perfected. As you know, a lot of companies, if you consider the truth separated from the hype, like Uber also kind of is not focusing a whole lot on self-driving as much as it was pushing a couple of years back because there are challenges towards that. But we are having different levels of autonomy being defined, like level 1 to level 5, and most vehicles are up to level 3. Like if you use any kind of a Tesla system, you will see by default you will get a level 3 autonomy where it can do a lot of the self-driving tasks. And obviously companies are investing heavily in automated like freight carriers like trucks and so on. So overall, basically what this slide is trying to tell you is that deep learning and machine learning are no longer just hype, or it's like you just take some sample data set and do something and that is the extent of it. Real world problems in the industry across diverse domains, if you see, we are not just talking about one or two domains, are being solved by AI based systems. And we are seeing a lot of problems related to anomaly detection as well as reinforcement learning, deep reinforcement learning being used for factory automation, smart factories, predictive and preventive maintenance, and different kinds of automation tasks. So basically, the possibilities are endless. And these are, again, other domains where AI is being used in some form or the other. I've definitely seen a lot of systems nowadays being used for sports analytics. And interestingly, sports analytics as a field itself has emerged. And we are also seeing courses being offered in sports analytics. So definitely, this is something very interesting that previously fields which were not leveraging as much data-driven intelligence are nowadays openly embracing it. And we are seeing new kind of jobs also emerging in the market. So, like I said before, deep learning is effective because it helps in automated feature engineering besides your modeling activities. It helps in learning a lot of features automatically in terms of representation learning, like in this case, for a convolution neural network, which can be used for image classification. It will automatically learn features ranging from simple generic features to very complex specific features in different layers in the network based on the depth. And it's not just limited to vision, you also have speech to text, text to speech systems, which are leveraging deep learning architectures like transformers, LSTMs, bidirectional models, and so on. And the most important thing, scale drives deep learning models. Larger your network and more data you have, you can get a model which can be generalized to solve different problems. The most recent example of this is transformers, where we have seen transformers being used to solve multi-tasks or multiple tasks in NLP, leveraging the same pre-trained model. So that is where scale definitely drives deep learning models. And other reasons why deep learning has become more effective now, we have more data, we have better compute like GPU, we have a lot of easy to use open source software, and we are getting the latest and the best models coming out almost every other month. So because of all this, deep learning has become very popular because neural networks as a field or as a technique has been there since decades, but only in the recent several years we have seen this actually being adopted in the industry. In terms of transfer learning, so the whole idea is if I already have some prior knowledge of solving a task, can I solve a new task? So that is where transfer learning is all about. If I know how to ride, let's say, a motorbike, it will be easier for me to learn how to ride a car. If I know how to play classic piano, I will be able to learn how to play jazz piano faster. And the most classic example, if you know math and statistics, your foundation is strong, it is not that difficult to then learn machine learning. If you know machine learning, it's not that difficult to learn deep learning. So that is where it's all about transfer learning, where the learning is not isolated, but it is basically shared. Like if I have built a system which can recognize different types of images using a large convolution neural network, I can take all the layers and the pre-trained weights, which is known as the knowledge of that network, and adapt it to my own problem, like let's say malaria detection, which I will talk about later on. And you can detect whether a person has a disease or doesn't have a disease. So that is where instead of training a model from scratch, even if you have less data, you can leverage a pre-trained model and often get a better performance. And the reason or the advantage here is training deep learning models from scratch can take a lot of time. You may not have enough data. And that is where pre-trained models have been trained already on a lot of data and can be specialized to perform specific tasks. You can use it to do feature extraction. You can use it to do inference. And nowadays you have models available in both computer vision as well as NLP like transformers. So that is where if you have less data, you can leverage some of these models and solve the problems in a really effective and efficient way. And these are models in deep learning. Deep learning for NLP, if you see, we have BERT, GPT, XLNet, all the latest and the best models from the transformers regime. In terms of the most popular architectures being used these days in most AI systems, we have convolution neural networks, which can be used for image or text classification. It can be used for audio classification, also audio detection. It can be used for object detection, segmentation. We have recurrent neural networks, long short-term memory networks, and gated recurrent units, which are all sequential models, which can be used for problems like time series forecasting, text classification, text generation. And then we have bidirectional models also, which process the sequential information in both front to back and back to front and helps in capturing better contextual information. We can use these models for a lot of sequence problems like building a parts of speech tagger or building a named entity recognition system, especially in, let's say, when I'm working with healthcare or financial data, which has its own named entities, and I need to extract them from documents or contracts, I can build my own NER model using a bidirectional LSTM. Autoencoders are very useful. They are more of unsupervised deep learning, and you can use them for image denoising. You can use them to learn representations from images and perform image search engines or similarity. We use encoder decoder models to solve problems like language translation, speech to text, text to speech, and transformer models. You already know they have beaten almost all the benchmarks in NLP. You can use it to solve almost any problem ranging from sentiment analysis, text classification, summarization, similarity, search. I mean, I could go on and on. So these are pretty much the major model architectures which are being used these days in the industry to solve most of the complex problems which are out there. Basically, these models are a combination of these models. Now I will start with the different use cases, which I will briefly talk about. I can't share everything for some of them, and I have modified some of them based on obviously a lot of the NDA clauses which I have signed. So the first problem is about predicting data center device failures. So if you think about any kind of a company which is operating at scale, usually any company will have some kind of servers or data centers along with interconnected network devices. So let's say when you are logging into Zoom, Zoom has a data center, which is basically enabling them to start the meeting, and then you are joining the link. If Zoom's data center goes down, this entire call can go down. So that is the whole point of it, that data centers are key infrastructure which are used by the entire enterprise or company. And most of the systems these days are reactive in nature, where if the system goes down, then the operations team starts to work on failures after they have already occurred. So the whole point here was, can we leverage historical data around device failures to predict future failures with a good enough lead time? So the whole idea here was, I shouldn't predict the failure after it has happened. Then that is pointless from a business perspective. The idea is, can I predict 6 hours in advance that based on the state of this system or this data center, looks like this server is going to shut down within 6 hours because of some parameters. And that is the whole point of this problem. So that is where we had around 3 terabytes worth of historical data, and this was time series data. Like imagine events A, B, C, and D are occurring over time. Now imagine you have like 50 or 60 of these events, and these events can be anything, like a connection is being made, some data is being transferred, uh, an application is running, an application is stopping. So any kind of an event which occurs in a computer, those are the kind of events I'm talking about. So we have time series based device events for the last couple of years. What we did is we had label data where we knew the timestamp when a failure had occurred for the data center. So what we did was we went 6 hours back from when the failure had occurred. We put a lead time also, so that let's say this is a 2 hour lead time. We go back 6 hours before that 2 hours, and we get all the time series events data for this stream of data. And this is known as a bad observation window, which means all the time series data which occurred in this window led to the failure occurring. Let's say that is the hypothesis. And all the interleaving windows, like let's say whenever the device was functioning normally and there were no failures before and after this window, that is known as a window of data when the device was good or no issues occurred for the data. And then what we did was we did a lot of manual feature engineering, like counting the number of events occurring over time, doing some sequential information also, like did event A, B, and C occur once or twice over time, those kind of things. We did some binning. So a lot of manual feature engineering wasted our time, but we didn't hit that level of performance which we were expecting. So that is where we thought of taking this time series data and binning it in 5 minutes each. So imagine you have 5 minutes windows on the x-axis, and your y-axis is all the different types of events which were over 30 or 40 events. And then imagine you are putting the number of times all these events are occurring over time. So this becomes like a matrix of numbers or like an image heat map, where if different events are occurring more at a certain point in time, the density will be more, or the heat map pixel values will be more densely colored. So we converted our events data into a multivariate time series data with x-axis representing the time and y-axis representing all the events, and the values representing the number of times the different events are occurring over time. So we end up having a 2D tensor for each window of data, like this is, let's say, a bad window or a good window. So now, basically, since this is a two-dimensional matrix, we can, instead of sitting and manually extracting features, we can just pass it through a convolution neural network so that it can take all the bad window images and it can take all the good window images and automatically extract features and find out the relevant patterns, which is, let's say, leading to the failure or making the device function normally. And that is where we leveraged convolution neural networks. This is one of the first CNNs which we had built. This was several years back when CNNs were just coming up from a software perspective. It was very difficult to still use TensorFlow. I think this was way back in 2015 or 16 when TensorFlow had just come out. So there were a lot of inherent challenges. So essentially, as you can see, we have 72 columns where each column is like 5 minutes worth of data. So 72 times 5 is 360, so 6 hours, and you have 44 different types of device events. And all this is doing is automatically extracting features for us and helping the model to classify it as the device will fail or not. And then we also leverage transfer learning in the future by reshaping the image and essentially passing it to a pre-trained model like a ResNet or a VGG and so on. And then finally predicting whether a failure is going to happen or not. And in this way, again, these are some high level numbers where we were able to get a hit rate of around 78%, and the false positive rate was reduced to around 10%. So, pretty decent performance overall, if you see, as compared to all the other general machine learning or shallow neural network models. So, that kind of shows you that if you have enough data and the right data, a deep learning model can definitely cut down on development time and also sometimes help you reach a better performance. Next one is around healthcare, malaria detection. The problem which we solved was more in the area of disease segmentation, not just prediction, but showing which part of the, let's say, body is having a certain kind of disease. But this is very similar to that. So the whole idea is, as you already know, malaria is a very deadly disease. It is prevalent in all the tropical regions, including India, given that they are in the tropical belt, if you think about it. So if there is a delay in right treatment, it can lead to complications. Definitely, it is a serious disease. So quicker you can diagnose malaria, the better it is. Now, why are we talking about AI here? What is the reason for it? Humans can only do this, right? So the reason is because the procedure to detect malaria is intensive. After you get the blood smear, you have to magnify to you have to magnify it to 100 times using a microscope. There are experts who have to sit and look at the structure of the cells, count the number of red blood cells, maybe, and then essentially come to a verdict. And now imagine in different regions, like rural regions or where people do not have access to healthcare as better as, let's say, in the major metropolitan cities. So that is where, if you can have some kind of an automated system and quickly flag some as suspicious, then maybe those people can be rushed to the hospital. And if it's a false positive, it's okay. But if it's a true positive, you are saving a life essentially. So that is where this is the kind of an open data set which was open sourced from an actual hospital or a collection of hospitals, where you have different blood smear sample images or scans, microscopic scans, which are labeled as malaria, where the person had the disease, and we also have the healthy cells. And the idea is, can we train a model to automatically process this and learn the pattern, so that in the future, if we give a scan of one of those cell samples, it will be able to predict blood samples, it will be able to predict whether the person has malaria or not. And that is where the process we followed was get the label data set, split it into your train, test, validation, do some pre-processing and image augmentation. As you already know about, you can rotate the image or crop it if you want. increase the contrast or brightness, add some noise, maybe like some Gaussian noise, so generate more data, and try out different models like training your own convolution neural network from scratch or using any kind of pre-trained models, which is basically transfer learning, and then compare the performance. So this is one of the models which had been used, one of the most simple pre-trained models by the visual geometry group at the University of California, which had around 19 convolution and fully connected layers. So we don't need the last few layers because this model was trained to classify uh, millions of images over 1,000 classes like cats, dogs, vehicles, and so on from the ImageNet challenge. All we care about is putting our own classification layers here to predict yes or no, which means whether the person has malaria or not. But all these layers, we leverage the pre-trained weights and fine tune it in the context of our own problem, which is malaria detection. And then these are the learning curves showing the accuracy is pretty decent, and the overall performance, we reached around 96% F1 score and balanced accuracy, which basically gave an all-around good performance to detect malaria accurately up to 96%. The next use case is slightly a bit complex, but I will try to talk about the main parts on this. So this is about, let's say you are using a software like Zoom, and Zoom is built on different libraries. And because every software is built using libraries, no one will sit and code everything from scratch. Now, let's say in that software, one of the libraries has some kind of a security issue, so a hacker can take control of your system. And these are not like this is not like a joke, it's a very serious issue. And every now and then you will suddenly see this in the news that this company's system was breached, or this software was said to have a fatal flaw which could be accessed by hackers, or these many passwords have been leaked. So these are real issues, and the idea for this use case was in the cybersecurity domain. We have all these open source software which is used for the context of software DevOps and machine learning ops, as it is known as ML ops. So those are libraries like Kubernetes and OpenShift and so on. And the idea is that these libraries themselves are built on top of 200 plus libraries. So if any of those are having a security flaw, can we find that out and do an early prediction or on the spot prediction that based on this version of this library, it could have a security flaw? Because when you're doing a university project, it's okay. But if you are building a software in the enterprise and customers are buying from you, if those issues are there, they should be notified as soon as possible before it becomes a huge a legal issue or even something worse. So that is basically the problem. Developers don't code everything from scratch. They use a lot of code written by others, which are the third-party libraries like TensorFlow, PyTorch. These are all third-party libraries. So these are known as dependencies, open source libraries and frameworks, which we use. As you can see here, like Keras, TensorFlow, NumPy, Pandas, all of these are libraries which are used in different applications for machine learning and deep learning. And if you see, the number of third-party libraries have been increasing exponentially for some ecosystems like JavaScript, and for other ecosystems also, it has been increasing at a steady rate, which means more and more software is being produced, more and more libraries are being produced to make the lives of developers easier. And that is where, because the number of libraries are increasing, the number of vulnerabilities which are being found every year also is increasing steadily, as you can see, because it's not like everyone can check the library for all types of attacks all the time. They will be pushing out features also. So that is where the vulnerabilities have also been increasing over the years. And the key objectives for this problem was to proactively predict what could be some probable vulnerabilities across direct or indirect libraries which are being used in the Golang, Kubernetes, OpenShift ecosystem, which is basically a bunch of products which, as some of you might know, like IBM and Red Hat are releasing in the cloud domain. So these are tools which can fast pace your development as well as help you scale applications very quickly. And the insight which we got was that public data can be tapped for insights here, because most of the time developers will be opening some kind of public issues that some problem is happening with this library. And often there will be also insights from the National Vulnerability Database, which is a security-based database from the US government, which consists of all possible security violations under the sun for each and every library. If something is found, they have to flag it. So we have that kind of text information. So that is where, again, I won't go into too much details, but talk about the essentials here in terms of what we did. We have over 850 plus libraries which we were tracking on a day-to-day basis. So imagine that there is a big product which has been built on top of all these libraries. And we were tracking each of the libraries here. And we used to monitor the GitHub repository for that library. We used to monitor public forums and mailing lists, as well as Bugzilla, where people file bugs. We used to collect all the text-based information from these sources on the web and then store it in a database. And then we pass this through our trained models, which essentially helped us in predicting whether there was a potential vulnerability or not. And how we did that was we constantly got a stream of label data also from our security experts who used to get the notification whenever there is a vulnerability released or not. So in that way, we also got some label data. It is not like everything was unlabeled from the beginning. And that is where we explored models like transformers, which is one of the latest models in NLP, which uses a stacked encoder decoder model. We used models like BERT, which uses only the encoder part of the transformer stack. We used other models also like bidirectional LSTMs and so on. So the overall workflow was monitor 850 plus library repositories being used by the OpenShift product, extract useful data like issues, pull requests, commits, comments, conversations, forum posts, pass it through the first model, which filters out data which is not relevant to security. And the second model helps us in filtering that if it is a security event, is it talking about a security enhancement or is it talking about a vulnerability or a hack in the system? And then based on that, the model was improved based on feedback from domain experts. And again, this is not a very simple problem because it's not like every library is having a security issue all the time. It is very rare. So if you see our data set had close to 200,000 different events of interest, and only 650 were like common vulnerabilities and exposures. So it was like a highly imbalanced data set. And that is where we used different models like bidirectional LSTMs or GRUs and BERT. And as you can see, we got a pretty good performance here with 80% of coverage and 71% of true positives. And these are real world numbers. It is not like some kind of a fairy tale where you will get 100% accuracy or something. And remember, again, our company is not going to be rewarded or congratulated if we correctly predict non-vulnerability as non-vulnerability. I mean, it is expected this has to have a high performance because if you start flagging non-security issues as security issues, it is extra headache for the security team. So no one is going to congratulate you in the real world for a high performance for this. This is expected to be this kind of a number, else no one is going to use your product. That is how the reality is in the industry. The key focus is always on this because this is something which, if it's true, it holds a lot of value. You are even able to, let's say, notify the owner of that repository. Like, let's say there is a vulnerability in TensorFlow, you go and notify Google saying there is a serious security issue and you need to fix it. And then you can get a reward for that in terms of obviously better collaborations and other aspects in terms of better integration with the products and making the products safer and more secure. Some other smaller use cases in the computer vision domain. So image super resolution, a very popular use case being used for image enhancement, like in image software, as well as other domains like security, surveillance imaging, medical imaging, image generation to better the quality of the image. So the whole idea here is if we have a small scale image with a poor resolution, can we blow up the image to, let's say, 4 or 5 times its size, but retain the quality of the image as a high resolution image? So that is why it is known as image super resolution, where you are resizing the image and blowing it up to 4 times its resolution, but still retaining the quality of the image. And that is where, again, I won't go into too much of the technicality given the complexity as well as the scope of this session, but there are some of the latest and the best state of the art models out there, like residual dense networks, residual dense network, which uses multiple of these blocks, as well as generative adversarial networks. And the whole point here is there is no secret. You need training data where you have low resolution images and you also have the corresponding high resolution images. And then you use one of these models to train the model, generate the loss, and then update the model with backpropagation. So essentially, you are training the model to learn patterns that if this was the low resolution image and this was the high resolution image, how do you get to the high resolution from the low resolution? So this is like an image generation problem where you are generating a complete image. You are not like predicting a class or something. And that is where we use the residual dense block along with a generative adversarial component to basically predict whether the final image which is being generated is true to the original image or not, which is the original high resolution image. And this is like one of the examples on the sample data, which you see where this was the original image, which is very small and the resolution is not so great. And once you blow it up, there will obviously be some artifacts, but you try to retain the resolution as much as possible. And that is typically the output being used in different areas like camera surveillance systems to blow up images and retain the quality. Like, let's say I want to track the license plate of a car from a CCTV footage, or it's used in medical imaging to get better quality images to zoom in and see where a disease might be affecting the body and so on. Neural style transfer, almost all of you may have used some kind of photo editing software. There are different apps like Prisma and so on, which make your images look stylistic and artistic. So that is the whole point. Like if I have an image, like a Taj Mahal image, and I have Van Gogh's painting, can I make a portrait style of the Taj Mahal in the same style? So it is basically an AI system which leverages deep neural networks and generative capabilities to generate a completely new image with the style aspects of a style image and retain the structure and the content of an original content image. And that is where it applies the style of this reference image to a specific target image, which is our content image, to generate this final stylized image. And at heart, it's an optimization model where it takes two images, a content image and a style image, and it tries to blend them together. And the main objective is to make sure that the final image retains the content of the content image, which means the structure of the main artifacts like these pillars and the whole dome here, it should remain the same. It should not get distorted. And the style of this image, like the texture, the color, the patterns, that should come in here without affecting the structure of the content image. That is the whole point of the neural style transfer model, which is at heart, again, an optimization problem. So we use convolution neural networks to extract the relevant features. We use a pre-trained model in this case to make the final system perform better instead of training a CNN model from scratch. And as you can see from the style image, we extract various style features like textures, patterns, colors, and so on. From the content image, we try to extract the structure or the overall outline of the image so that we can retain the structure. These are more of the technicalities which talk about which layers we use to extract what kind of features and then basically combine them to build that final image, which consists of the style components and the content components. And this is like an example where if this is your original content image and this is like a style image, you're trying to propagate the style of this into this image. And then you have different artifacts also where if there are additional noise being generated, you can use something uh, for reducing this loss using the TV loss, which is the translation variance loss, and you can slowly create a better quality image. So in that way, style transfer helps you get better performing visual stylized images from a source image and a source style image. And the last use case which I want to cover before I conclude my session is around anomaly detection, which is a very popular problem in the industry. So basically, in case of time series data, can you identify a huge spike, which can be leading to some kind of an issue in a system, a device, be it in manufacturing, in the infrastructure, wherever. So that is where the whole idea of anomaly detection is to detect these spikes on the fly. And the model which we used was the seasonal hybrid model, or seasonal hybrid ESD model. ESD stands for extreme studentized deviate, which uses the student's distribution, also known as the T distribution, over a time series to generate, or rather detect and flag the anomalies. And the whole point here was, for each data point in the time series, you compute the G score. This is the grub score, which is an absolute value of the Z score. Find out which are the points which have those highest scores. And then based on a threshold, which is a significance level, find out whether it is an anomaly, flag that anomaly, remove that point from the data, and continue the process till you get all the anomalies. And that is where we had a wide variety of data, as you can see, from performance data, server log data, application logs data. All this data goes into Elasticsearch system, which is kind of like a NoSQL search-based database, which dumps in all these events data. And then we built an anomaly framework, which consists of different models like seasonal hybrid ESD, weighted moving average, concept drift, forecasting models, threshold-based models, deep learning models, and then whatever was flagged as an anomaly, we updated the Kibana dashboard, which were used by the operating the ops team to operations team to find out whether those anomalies are useful, give us feedback to improve the model, and so on. So overall, these are, I think, I covered a lot of use cases in a short amount of time, but given that we didn't have a lot of time, hopefully this gives you an idea from a perspective that AI is definitely no longer a hype. These are all real problems, which I talked about today. And these are all problems which have been solved to a degree, but not perfected. So that is where companies are trying to build better models, use the latest techniques to see how you can build more efficient and better performing models to solve diverse problems in the industry. So yeah, that brings an end to my session. Hopefully this was useful, and yeah, can take some questions maybe now. So if I see the chat, I can see a few questions. So let me quickly take a few of these. Do we have time to take a few questions? Okay, great. Yeah, thanks for the feedback that you're finding it useful. So let me see. Let me take it from the beginning. Common examples of reinforcement learning in the industry. I think we covered this in terms of manufacturing, smart factories, algorithmic trading. Definitely, these are real world examples. Otherwise, RL is used mostly in gaming, as you know, to build automated systems in gaming. And again, that is a very niche domain. So, not really you can consider like a regular industry use cases, but otherwise, definitely automation in factories and manufacturing, we are seeing a lot of examples of reinforcement learning being used. Okay, Akshay is here. Great to see you, Akshay. Yeah, importance of data visualization is very important for sure. Like, let's take a non-traditional example. As you know, if you're working on a tabular data set, obviously you can look at your scatter plots, you can look at your bar charts and histograms and decide that, okay, if the histogram of people who committed a fraud transaction versus a non-fraud, what kind of insights we can get. Sometimes you can get some real insights there. So that is where data visualization is very important. But even in non-traditional examples, like let's say speech data. So recently, I've been basically advising someone on a project for music genre prediction based on audio data. And that is where we saw some clear patterns on the visualization which you can generate from audio data. As you know, like audio data is basically data which occurs over time with some frequencies. You can basically extract that and visualize it as a Mel spectrogram, which visualizes it as a kind of like a visual image representation. And you can see clear patterns in terms of where there might be noise, where there might be some definite peaks and valleys. And using that, you can even understand that are there genres which can be very difficult to maybe classify, or are there genres where you may need more data? So data visualization definitely important in that context, no matter what you're doing. But again, it's not like you will always need it. If you're working on NLP problems, EDA is not as important as other kinds of data. What is the most complex work of a data scientist from day to day? It varies. Some days you might be breaking your head just to get some data. Some days you may need to clean the data and it may take a lot of time. Sometimes you may need to think about what is the best possible model which you can apply, because no one in the company will usually come and tell you that this is a problem, apply a random forest model to it. The problem statement will be very vague. Figuring out what is the right solution to the problem is something which is an art as well as a science, and that is where you as a data scientist are expected to do that. And some days you may be building models for a fair amount of time. Some days you may be presenting your work. So everything is important, from technical skills to soft skills. How to go about fine tuning models in the domains of images text forecasting, this is a pretty big question. So for fine tuning, again, if you're using in images, you can use any of the pre-trained models like ResNet or VGG. You can fine tune a few layers. You can fine tune the full model also. You may need to fine tune with a lower learning rate. You will get a better performance usually. For text, you have models like transformers. You can pretty much fine tune them very easily. Check out the Hugging Face Transformers library. And there is also other wrappers like simple transformers with less than 10 to 15 lines of code. You can solve a lot of problems on that. Forecasting, honestly, I haven't done transfer learning in forecasting, so I wouldn't be the best person to answer that. What steps we need to follow to retrain the model? You need a human in the loop process. You need to store your new data coming in. You need to label that stored data. Then you need to update your model based on an online or a batch mode and retrain the model. For someone starting in data science, which is the growing domain, is it deep learning, NLP? I would suggest start with fundamentals of data science, understand how to understand data, understand what is learning, understand machine learning first, then go into deep learning, computer vision, NLP. So the main thing is, like 5 years back, maybe those were specialized fields. Nowadays, to make yourself attractive to employers, pick up diverse skills. Basically, follow that T-shaped model, as Andrew Yang says, like broaden your skills as well as the depth as you get time. So machine learning, deep learning, computer vision, NLP. I have done all of them. Again, I'm not an expert in everything, but the larger breadth you have, the more attractive you become to basically go into any company in the future. If someone has 10 years of traditional software development experience, which one you suggest? I wouldn't be the best person to say that, because it is not like anyone with 15 years of experience. If you do deep learning, you are guaranteed a job. So you need to learn everything, to be honest, so that you can apply it. But again, if you're targeting traditional firms like banking and finance, I would start with machine learning rather than going into deep learning. So it depends on the domain and the industry. Okay, so what else? How can we mimic a human voice given a sentence to be spoken in another voice? I haven't done this, so I'm not an expert, but I have seen a lot of speech to text and text to speech models being generated. And nowadays, we are seeing a lot of models like Wave to Vec coming out from Facebook and so on. So, as long as you have enough data, you can train some of those models, which are based typically on like a CNN plus RNN architecture most of the time. I haven't dived into the Wave to Vec 2 paper, so I wouldn't be an expert, but those are the kind of model architectures you need to check out, which are based on, again, sequential models, either transformers or CNN plus RNN or CNN plus LSTM. And as long as you can structure your data in the right way, it should be doable. But again, if you don't have enough data, there will be issues. Okay. So what else? Filter events based on text and context. How can I proceed? Depends. Again, this is very vague. It will depend on how you can do this, honestly. So if you have different events and you know the conditions to filter, you can use regular expressions. You can use machine learning itself to do a prediction and filter and so on. So it really depends. Many tools for model deployment. What should be the rationale behind choosing a tool? If you're working in a company, choose a tool which has a very active open source community which has been there for at least a year maybe, and which has a good community support, or if it has enterprise support, because if things start failing, no one will be there to help you unless you get a good support from the open source community or the people who have developed that library. Okay, so hopefully that answers most of the questions. Anything else, let me know. And again, thanks a lot for attending the session. I'm glad all of you found it useful. Yeah.
Thank you, Dipanjan. One more question is there from Harshita, who is first year student. She is
Oh,
asking if
okay, I
we are
missed it.
freshers, yeah,
Mhm.
what kind of roadmap you would like to suggest for them?
Okay, I think you'll find a lot of roadmaps online, so definitely check it. But from my side, the recommendation would be have a minimal learning framework. Like you should know enough linear algebra in terms of what are arrays, what are matrices, what are tensors. You should know the basics of matrix multiplication, dot products. You should know basics of differential calculus at least, so that you can understand gradient descent. You don't need to sit and become a statistician. So know the basics of statistics, descriptive statistics, and inferential statistics like A/B testing, t-test, z-test, bootstrap test. I think that should be a good enough foundation. Then you need to understand different types of data. This is something which I have been emphasizing since the beginning. I have talked with a lot of people where sometimes they say that, oh, this is text data. I haven't studied NLP. In a company or in an interview, if you say that, that is a sure shot, basically rejection. So you should know how to handle different types of data. Doesn't matter whether it's NLP, computer vision. You should know how to handle numeric data, how to handle categorical data, how to handle image data, how to handle text data. Those are the basics. So data processing, data understanding is very important. And then feature engineering, you should know different methods for feature engineering. Then feature selection, then understand different types of models in machine learning, understand the advantages, the assumptions, why should a model be better than another model, or why is this model not that great a model sometimes. So you should be able to answer those kind of questions. So essentially, whatever I'm telling you is the whole process, industry standard process for data mining, understanding the data, understanding how to clean the data, exploratory data analysis and visualization, building machine learning models, knowing how to evaluate and tune the model, knowing different types of hyperparameter tuning like grid search, randomized search, Bayesian optimization. If you know all of this, you are almost there with your fundamentals. I would emphasize you to also spend a fair amount of time for um, model deployment a bit, like focus a bit on the engineering activities. It is definitely very important. So you should definitely know the basics of how can you deploy a machine learning model. And you can just search like, how do I deploy a scikit-learn model? That is a simple thing you can start with. And once you do that, then you can basically go into other areas like deep learning, natural language processing, computer vision. So I would start with those fundamentals, and then I would go into the advanced areas. And if you just search a roadmap for machine learning, you'll find a lot of things. But as long as you're following this structure, that is what will help you. And again, follow a hybrid approach where you are learning the concepts, but not just reading pages or watching YouTube videos forever. You should also apply the concept. Like if you're learning about EDA, do a Jupyter notebook on an open data set for data visualization. If you're learning about logistic regression, apply it on a data set. In that way, you will be sharp in terms of your practical skills as well as your conceptual knowledge. So that will be my advice, at least based on what I could answer you in 2 to 3 minutes.
Yeah, thank you, Dipanjan. And yeah, it was an indeed very informative and insightful session for all of us.
Sure.
And to all the participants, thanks for attending this session and thanks for raising very good questions that all of us were eager to hear from Dipanjan. And one more announcement that the link for feedback form has been posted here. Please fill that form and then participation certificates would be received on your email IDs automatically. And one more announcement with reference to our next session, which is arranged in the next week, that is hands-on workshop session. On 2 days, it is arranged on the topic called as visualization with Tableau. So you may also register for that session and get more hands-on related things on data visualization, which is much needed in the industry nowadays. Okay, so with this note, I would like to thank you all the participants, our guest of honor, Dipanjan, and looking forward to more such sessions here. Thank you again. Good day.
Thanks a lot, everyone.
Yeah, thank you. Bye-bye.